in a complete circuit, whenever they experience a change of B field, right? Whenever they experience this, according to Lenz's law, they will want to oppose the change. So if you say more B field from North Pole, more B field going in when you move closer, they want to make it less. Okay? So this is oppose the change. And how you oppose the change is oppose the change by, this is the second part, by inducing the current in it. Okay? So maybe we did this exercise last time again. But if I ask you, if I pull this in, how should the current be in this coil? Go up or go down? It should be next to Faraday's. Page 30. Okay, let me guide you through. You're going to listen very carefully. If this magnet go in, we only look at the north pole, because north pole is where the B field come out, right? North to south. Yes. So only look at north pole. If more and more north pole go in, then according to Lenz's law, they want to make a B field that go opposite. That means here, Lenz's law. Opposite. That means the B field, it want to generate like this. How can we generate a B field like this? We can have current inside the coil, but how do we determine the direction of current if we know B field already? Use the which hand? Right hand what? Right hand grip rule, very good, right? So the B field is a thumb, and the grip is a current, so go like this. So the current should go up, and you check. Anna, you B field this one's fine, right? B field, right? And you grab like this. No, I'm talking about the outside wire. How about this? Because this is 2D and your hand is 3D. You grip like this. So just now I was talking about this part. So for this part is going, this makes a loop, right, of the current. So if you only talk about this part, then it's going up. If you're talking about the one behind, it's of course down.
How do you tell?
Just grip it. So this one go in. Depending on which part of the wires I'm talking about. If I only talk about here, then going up. This part going in, this part going down, this part going out. This is a circle. Yeah, exactly. Any questions? So let me try to move this. 3, 2, look at the blue dots. 3, 2, 1. It moves down. Why does it move down? Why not go up? Why do they move down? Lenz's law? It's not about Lenz's law. No, it's not about that. Okay, let's look at this again. We just conclude the current should go up. But when in this simulation, when I go in, guess he said again. Just say what he said. Very good. The blue dots are electrons. And what we deduce are correct. Currents go up, but the electron flow will go down because simply just opposite. We talked about this last chapter. Okay? So, can you tell me what happens if this magnet is leaving on the right hand side, leaving the coil? According to Lenz's law, what should happen to the current? So you mean the current should go down? Just not go up, right? On this wire. Now it's go down. Is that correct? Okay, listen to me. This part is really the most difficult in IGCSE. I heard from previous years. Like among all these chapters. Later chapter is easier. Like logic gate, nuclear physics is easier. This is the most difficult. When you're leaving, you have from the magnet, you have more or less B field. Less B field, right? And according to Lenz's law, for some reason we don't actually know why, but what this coil want to do is oppose a change. Since you have less, they want to create more, right? To this direction. To this direction. We just find out experimentally. You don't know why. That's why I call it law. We don't know why, but that's the nature pattern to find out. We want to create more B field by this coil, and in terms of that, then you use the right hand rule. You grip like this. That's why the I is downward. B, and you grip like this. That's why this one is downward. Check it out, you think about the previous case. Previous case is when the magnet is here, you're going in. More and more B field towards this side, and you want to oppose it. You want to make a B field that opposes it. So that's why it's going up. It's opposite. B field to this side, opposite. Now, since you're leaving, less B field. This coil want to create more B field. So that's why grip like this. Grip like this meaning that the current go down. And what about the electron? The electron move up. Question? Yeah, see it. B field, what do you mean?
Like because the magnet is going, like the B field is going that side.
To the right.
So shouldn't the
Opposing what?
shouldn't the opposing B field be here?
Be that way?
Yeah. 唔係佢話講呢度係 weak 咗，即係講呢度 weak 咗，所以一定要 strong 嘛。即係好似你咁樣入嚟嗰陣時要 strong，所以好似係。我覺得講唔係咁如果你咁諗，如果你 weak 啲係呢度兩個係 weak 啲，佢呢啲先 strong 啲。係我都係咁諗。係我都諗到。係啊係啊，唔係你 direction 嘅 opposite。
Because at the end the B field is like this, right? We draw something like this before. North to south, right? North to south. So at the end, at this point, it's still going back to the magnet, so it's still pointing that way. So since you're leaving, weaker and weaker B field will be pointing that direction. Yeah. So my advice is just stick with the north pole, ignore the south pole. When you are trying to deduce, it will give you less confusion. Okay. So I'll show you with the experiment as well. The thing is, you just need to get the direction correct, right? So if current goes down, then the electron should move up, right? So let me have a look. Ready? 3, 2, 1. When it's leaving, then let's go up a little bit. All right, try to do it again. When you move in, the electron move down. In the middle, almost not moving because you are not really changing the B field a lot. When you're leaving, the electron move up. That means current go down.
So can I treat the electrons as like a solid pole? And then when it comes, the transfer line, these
I think that would be too complicated.
No, that's
Wait. Is there like a hand low?
No,
Oh.
no. It's already the most simplest way to.
With the soul going.
Okay. Good point. Richard want to ask, what if now this magnet go back in? The movement go back in like this.
Go down.
So what does it experience?
Current go down.
It experience, well, the B field is going that way. So it experience stronger and stronger B field going that way. So this coil want to oppose it to make a B field go where? Go stronger and stronger go that way, right? So they want to oppose it, so they would go opposite. Yeah, stronger and stronger go that way. So they want to go opposite. That means opposite that way. In order to do this,
oh yeah, the direction.
in order to do this, then how should the currents be induced? Go like this, great. So this should go up. Yeah. Yeah, go down. Electron go down. So this is correct. It will keep going the same direction until I move in the middle. Alright, and then once I keep going, it will go opposite. Okay, I'll show you again with the demonstration.
So is it the length law? The length law is referring to the electron inside.
We refer to current only.
Oh, because whenever the current goes, like for example, with this one, the current goes up, the electron will go to opposite direction, goes down.
The reason why currents go opposite to electron flow is just the tradition that we design. We learned in the previous chapter in circuit. People define in a circuit that this is how the currents come out. But what happened at the end, we will realize it's an electron moving opposite direction. So that's why simulation kind of a bit confusing when you look at the direction of current and the electron flow are opposite. But that's what happened in reality as well.
So you have to explain about this tradition.
Yeah.
How, like conventional.
Explain what? You may explain Lenz's law on this or this one? This one? No. This is just a definition. Opposite.
But the length law is referring to the magnetic field.
Yeah, Lenz's law is talking about how these want to create the currents. This current actually creates a B field. Whenever there's current, there's B field, right? And this is supposed to oppose whatever you experience in B field. I'll show you again in the demonstration. Can you pause the video? Can you guys come over here? I'll show you again with